Okay, you guys remember talking about strong electrolytes and weak electrolytes, and then we had the light bulb we put in the different solutions, and what was the difference between a strong electrolyte and a weak electrolyte? What happens at a molecular level that allows them to conduct electricity?
They are soluble.
Yeah, but sugar is soluble and it's not electrolyte. They deionize in water, meaning they split into their different ions, so there's charges floating around in the water, and they're able to conduct electricity. So they totally deionize. Same definition for acids and bases. We have strong acids, strong bases, weak acids, and weak bases. Strong acids completely deionize. They are completely ionized in water, meaning they completely, all the hydrogen breaks off of the anion and they're totally separate. So they are strong electrolytes. Their conjugate bases are very weak. So as the strength of an acid goes up, the strength of their conjugate base goes down. So very strong acids, it's very easy to lose that proton, very hard for it to gain it back as a base. These are the strong acids: HCl, HNO3, HClO4, H2SO4, HI, and HBr. You need to know those. So if you want to jot those down, but you need to know this because when we learn to, like if we have a solution of hydrochloric acid to solve for the pH, for a strong acid is different than a weak acid. So you have to be able to recognize whether it's a strong or weak acid.
Are those strong acids?
Those are the strong acids. All the rest of them are weak. So a lot of weak acids, not very many strong. It seems like there should be one more. Hold on. One? I thought there were 7. 6. HNO3, HSO4, HClO4, HCl. Nope, there's just 6. Okay. So I don't know if this helps, but for the periodic table, there's 3. If you look up there, there's 3 that are oxy anions: the NO3, ClO4, and SO4. So on the periodic table, they kind of go NSCl. So this is just how I remember them. I'm just telling you, you can have your own. You can make a saying. I don't care, but those 3 right there, they're right next to each other. NSCl. So HNO3, HSO4, HClO4, the most oxygens that it can hold. Those are strong. And ClBrI, right down 17, or down the halogens. ClBrI, HCl, HBr, HI are your strong ones. That's how I remember them. You guys could figure out something else if that doesn't work. Weak acids, when all the other acids are weak, and they only ionize a little bit. So they do change the pH. They do have a pH, but it's very weak. And so we will learn Monday how to calculate pH for weak acids. They have very strong conjugate bases, though. So their conjugate bases are very strong. Most acids are weak acids. What note is that? F. I'm guessing F.
It's a 7 quarter flat.
You think? I think it's an F.
I think it's an E.
I think it's an E.
Jay doesn't even know music. She can't even spell music. Stop playing.
I don't think I can make it beep without turning it off. So here are the strong acids. So perchloric acid, sulfuric acid, hydroiodic acid, hydrofluoric, hydrobromic, hydrochloric, and nitric acid. And these are the weak acids and then extremely weak acids. This doesn't include all of the acids. This is just a list in your book, okay? Strong bases, again, ionize completely in water. So the cation and hydroxide completely separate, and all of the molecules at base would completely separate. Strong electrolytes, the hydroxides of the alkali metals and alkaline earth metals. Where are the alkali metals and alkaline earth metals? Group 1 and 2. So hydroxides of groups 1 and 2 are the strong bases, and all the rest of the bases would be weak. Any other base is weak. Weak bases, incomplete ionization. So if you have 20 molecules in a solution, maybe 2 of them would ionize and the rest of them don't. So there is some ionization, but not all. And they are weak electrolytes. We said all of their hydroxides, all of the bases. So this is showing that as the acid strength goes up, their conjugate base strength goes down, because the strong conjugate bases are on the bottom here. Strong acids are on the top here. Here's a picture of strong acids. The acid is HCl, so if you notice, the orange is chlorine, and then all the hydrogen that came from HCl is on, like here's a hydronium right here, here's a hydronium. Can't see the white, but here's a hydronium very well. So all the there's no HCl molecules together anymore. Whereas for a weak acid, HF, this one is ionized because there's just the fluorine here and here's a hydronium, but this molecule has not ionized yet. So if there's a question about what are the major species in solution, for a strong acid you would have chlorine, the chlorine ion, water, and hydronium ion. That's the only 3 species that are in there. And then for a weak acid, though, you have fluoride, you have hydronium, you have water, and you have hydrofluoric acid still floating around. Does that make sense? Okay. So that's why the pH is going to be a little different for the calculation, because for a weak acid, we have to figure out how much of it actually deionizes, or ionizes, and then we find the pH based on how many hydronium ions are formed. For strong acids, all of the hydrogen forms hydronium, and we don't have to do that little calculation part. Oh, here's how it splits there. Here's the concentration of hydrogen and chlorine. There is no hydrochloric acid left, whereas here there's some hydrofluoric acid left and just a little bit of hydrogen and fluoride. Okay, identify as a strong, weak acid, or a strong acid, strong base, strong, or weak acid, or weak base. Strong acid, I'm just going to put SA. How about this one? It's weak. Nitric acid is strong. This is nitrous acid.
That's pretty weak right there. That one's pretty weak.
D?
Weak.
Strong base. Why strong? Sodium is in group 1, right? So it's a strong base. How about D? Strong acid. And this would be a weak base, yes. Questions on any of those? Which one is stronger? I don't know. These are. I thought they were going to be like their acid and conjugate base pair. Can I switch something? Let's change this to a 3, and then I'm going to change this to. Oh wait, no, they're both acids. It says acids on there. Hold on. That's just a bad question. Let's skip it. Because you want to have one be a strong acid and one a weak acid. Because, yeah, you'd have to look on a table. Well, does anyone have their book with them? It's in chapter 15. Oh, I would take that. No. Ooh, maybe right there? No. Keep going back. Back. Ooh, try 677.
Once we have the ribbons on,
Yes. But this isn't an exhaustive list. Like, H2OS isn't on there.
H2O is.
Yeah, this is a bad question. Okay, now we need to find the pH. So let's go through, we're going to go through several examples of this because it's asking for the pH of a 2 times 10 to the negative third molar nitric acid solution. So nitric acid, this is a strong acid, correct? So if I have nitric acid, what happens in solution? So we have H plus NO3 minus. And if I have 2 times 10 to the negative third molar, what's my concentration of hydrogen?
It's got to be number. 2 times 10 to the negative 11.
You use your coefficients just like you would do stoichiometry. It's a 1-to-1 ratio. So the concentration stays the same. The number of molecules, well, the number of molecules would be the same too. Now the mass would not be the same, but the number of moles of each, the concentration would be the same. What about nitrogen? Now, it really doesn't matter to solve for pH because for pH we're just looking at the hydrogen concentration, but what would be the concentration of nitrate?
2 times 10 to the negative third.
All right, it's still 1-to-1. It's still a 1-to-1 ratio.
So why'd you do if it was like 1 to
We'll do one. We'll just make one up. So, pH, how would I find the pH? It's the negative log of my hydroxide or hydronium concentration. So negative log of 2 times 10 to the negative third.
Already dropped the answer. That's like 2.6. No, 2.70. 2.70. That's right. That's right.
But it's 2.69.
8.
Actually, we should just have one decimal.
0.7.
Questions on that one?
No, man.
What about, okay, we have barium hydroxide. Is this a strong base?
Yeah.
Yes, so strong base, so we can calculate this more quickly. We haven't learned how to do weak bases yet. So I have barium hydroxide is going to change into ionize into Ba2 plus. We have 2 hydroxides, correct? And the concentration is 1.8 times 10 to the negative 2. So barium concentration is multiply by 2, right? Because if we had barium here, I'd put the coefficient for barium down here and the coefficient for hydroxide on top. So multiply that by 2. -2. So now I need to find the pH, though. There's 2 ways we can do this, because now we have the hydroxide concentration, not the hydrogen. So we could either solve for pOH and then subtract it from 14, or we can use Kw and divide by the OH to get hydronium concentration. Okay, so you want to find pOH. So we're going to find pOH is equal to the negative log of 3.6 times 10 to the negative.
You get 1.44.
44? Okay. So to find pH, you'd want to take 14 minus the 1.44. There you go.
So can we do it however way we want?
Yep, you could do it either way. You'd get the same answer.
You won't say like on the way through this way.
Mm-mm.
No.
Any questions on solving those?
No, ma'am. Done?
I have a question. Not on that. Will you put a review sheet? Is there a review sheet for the quiz?
For the quiz?
I don't
No, but I could maybe look and see if put a review quiz on Angel for the whole chapter. Like it would be the test one, but you could just pick and choose the questions.
Yeah.
Okay, last thing today is the monoprotic and polyprotic acid. So a monoprotic acid is an acid that donates only 1 proton. So in the formula, there's only 1 hydrogen, like HClO4, HCl, HNO3. There's only, it ionizes in 1 step because there's only 1 hydrogen to ionize. Whereas a polyprotic acid, oh, here we go, there's that. What was what? Yeah, it's just the ionization of hydrochloric acid. They have water in there because in order for it to ionize, it has to be mixed with water. And then they use hydronium instead of just H+, but when we did it, we just took the water out. Polyprotic is an acid that can donate more than 1. So you can have diprotic or triprotic acids. So H2SO4 is a diprotic acid because there's 2 hydrogens. H3PO4 is a triprotic because it has 3 hydrogens. So H2SO4 actually ionizes in 2 different steps. The first step, it's a strong acid, so all of the H2SO4 ionizes into HSO4 minus and hydronium. But then this HSO4, a little bit of this, since it's a weak acid, the little bit of the HSO4 ionizes to give us sulfate and hydronium. So the species present in this equation, there's no sulfuric acid left since it's a strong acid. All of it dissociates, and it's H. So the species is HSO4 minus and hydronium. But then a little bit of this also just dissociates, so we have some sulfate in there also. Yeah. Take the H off one at a time. So diprotic has 2 protons, triprotic has 3. And we'll do weak acids on Monday.